We are from the Group 1. Today we want to discuss about the group project computer architecture. We group have the 6 people. There is Tang Hong Sun, Jeffrey Dang William, Tan Zhao Yang, and it's me, James Law Xie En, Kang Rei Hong, and Eldrick. In this project, we will discuss the two tests. The first one is implement a simulate RISC CPU simulator with a custom instruction set and full phase discord execute cycle, initializing register and memory change. In test 2, we discuss build a cache simulator to compare mapping, mentor, and replacement policy, measuring hit or miss rate and performance. Uh, Now we start the test one. That is, what mean is the RISC? RISC stand of Reduced Instruction Set Computer is a CPU design that focus on simplicity and speed using a small set of fixed instructions. Their instructions are simple and can usually be grouped in one clock cycle, which make the procedure more effective and easily to pipeline. Another key function is store architecture. Only the write and store instruction access memory, where all other instructions operate on register. This improves the speed because working with register is much faster than accessing memory. RSC architecture are used in many real-world systems, especially in ARM processors, which are found in smartphone, tablet, and embedded device. Then this picture is show that this is a basic architecture for our RISC CPU simulator. The program counter PC point to the next instruction in memory. That instruction is logged into the instruction register IR. The IR decode the instruction and interact with a register R0 pergi to R3 to get a store value. The other performance operation like ADD of SUB using data from the registering. The steps are similar to the full fashion decode execute cycle. And we continue to discuss this 5 instruction set. The program counter is PC have the 60-bit and the use is track the address for the next instruction increment by 2 per cycle. And the next one I also have the 60-bit. The use is hold the current instruction begin execute for decoding and execution. In the next one, the register R goes R0 to R3 or 4, formatted by 8 bits. The use is general purpose register for temporary data store. In the next one is the memory, also have the 64 bits. The store instruction and data is 8 bits. And the next one, last one is AUR. The AUR is performance arithmetic operation to support to ADD and SUB. Then implementer code logics.
Okay, we start with an overview of support instruction in RISC, short for Reduced Instruction Set Computer. Each instruction is simple and typically complete with only one clock cycles. Our instruction set include load with opcode 0 times 0 with format load are the register destination address. Description will be load value from memory address into register RD. Next is store with the opcode 0 time 1 with format of store, RS, and address. The description of it will be store value from register RS into memory address. Next is add 0 time 2 in the format of add RD, RS1, and RS2. The description will be add RS1 plus RS2 in the store result in a register destination. Next is sub 0 time 3 in the format of sub RD, RS1, and RS2. The description will be subtract RS1 from RS1, RS2 from RS1, and stores in register destination. Next is jump 0 time 4 with jump address of format with that sets PC to address and with jump to instruction. Next and final will be halt with 0 time 5 of opcode with the format with only halt. It purpose is to stop the execution. Next is instruction format. Field the first field will be in opcode with the bits of 15 to 12. The purpose will be only for 4 bits, support up to 16 instruction. Next is destination register 11 to 10. The purpose will be 2-bit, select R0 to R3. Next is source reg 1 with the bits of 9 to 8, 2-bit for add or sub. Next is source rec 2 will be bits of 7 to 6 with purpose of 2 bits for add or sub, just like previous source and rec. And finally will be address with the bits of 5 to 0 with the purpose of 6 bits for load or store or jump from 0 to 63 range. Next will be the instruction cycles. The first will be fetch, that purpose on to read 16-bit instruction from memory PC. Next is decode to extract opcode register and address. Next is execute, perform action with the example that is add or load. And update will be PC plus equals to unless it's halt. Next is about instruction encoding examples. Take the first instruction here, load R0 with 0 time 10. If you encoded it, will be end up with the hexadecimal of 0 times 0010 with the explanation that opcode add will be 0 times 0 if RD of 0 and address of 0 times 10. We'll skip the load R1 with 8 instead. Add R2, R0, and R1 if encoded with hexadecimal will be 0 times 2840 with the explanation of opcode add will be 0 times 2, RD is 2, RS1 is 0, and RS2 is 1. Next is store. R2 with the 0 times 12 encoded hexadecimal to 0 times 1812. The explanation of it will be opcode store 0 times 1 RS to 2 equals to 2 and address is 0 times 12. And finally, final instruction will be halt with the encoded hexadecimal will be 0 times 5000 with the explanation of opcode being 0 times 5 with no operands. Now let's walk through the simple program stored in memory. This illustrates how a small set RISC instruction can perform complete operation with the demo. the when the address is at the address of 0 times 0 0, we load R0 with uh 0 times 10 address, memory address, and then at 0 times 0 2, we load R1 from 0 times 1 from memory uh, address, and then at 0 times 0 4, with 0 times 0 4, we add two value with add R2, R0, and R1, and then we store the result in R2 to the memory address of 0 times 12 in the 0 in the address of 0 times 0 6. Finally, once we reach 0 times 0 8 address, it will be halt.
Going sir, I'll be presenting step by step on how our RISC CPU work by one of the example addition between two values. So first thing first, we will hard coded the values into the memory. So the memory with address 10 is initialized with value 5, and the memory with address 11 is initialized with value 10. And also the PC is set to address 00 is where the first instruction will be coded, will be fetched, and all the register R0 to R3 is set to 0. So our program involves five steps. So the first step is fetching the value from the memory 10 into the register 0. Yeah. So moving on to step 2 is also fetching value from this time from memory with address 11 into register 1. Then the step 3 is addition between two values from R0 and R1, and then the result will be stored to R2. So step 4, we will be storing the result which stored in register 2 back to the memory with address 1, 2. And then all the program must be ended. So step 5 is about halting the program. Program is run. So first of all, you will see the menu. There are two selection. For the sake of this presentation, we choose two. So this show, after you click enter, there are many things that are pop up. So this thing shows how the RISC CPU stimulation is run. So yeah, this done by this function initialize memory. So we have hard coded all the instruction here. So after it finish initialize, it will be run. So if you are not satisfied with it, you want to build your program, then you can choose the first one, where you can write your instruction and write your data, and there's an example that you can follow. So moving on to the conclusion. So from this project, we have deepened our understanding about the architecture of RISC CPU. For example, the important components such as program counter, instruction register, and also arithmetic logic unit. A second thing, we have deepened our understanding about the utilization of instruction. We have seen how a 16-bit instruction is partitionized into many parts, and how each part can contribute to the performing of arithmetic and storing results and many more. And also we have learning by execution. So since all the program counters and register are visible to us, so we could see what happened and learn more. So there are also challenges that we face during the project. So for example, instruction decoding field, because our memory can store only 1 byte, but our instruction is 2 byte. So we come up with a solution which use a operator of bit shifting from C program. So the second challenge is wrong bits decoded. So to solve it, we use mask. So the third challenge is the stimulation didn't stop. So it is due to because we forgot to include the hot instruction. So yeah, it could be just solved by including a hot opcode. Yeah. And then about what our group members do. So for the question one, James, Eldrick, and me are responsible for question one. So in this project, James is in charge of designing the architecture of the CPU. So me is in charge of writing the program, and Eldrick is in charge of writing a simple program. There's two, which is one is addition of the two values, and one is on the program, which is subtraction between two values. So yeah, on also the presentation and the report is separated among us. So like this, yeah, that's all. Thank you.
Okay, now I need to present our project question to task to cache simulation. Next slide is I need to present what is cache memory. Cache memory is small, large, high-speed storage area in computer. There is smaller and faster memory that store copies of data from frequently used memory location. So there's various independent cache in a CPU which store instruction and data. The picture below is show that the computer system cycle will have CPU, cache memory, primary memory, and secondary memory. Okay, next I need to present what type of cache memory. First one, L1 cache that is incorporate directly into the CPU. The size is around 2 GB to 64 GB. That is depending on the processor type. For example, in the item called i5 processor typically range from 32 GB to 64 GB. While L2 cache is larger than L1, often found in a core processor or standard logic chip is linked to CPU via a high-frequency system bus. For L3 cache that is designed to enhance L1 and L2 speed, typically slower than L1 and L2 but faster than DRAM. DRAM is stand for Dynamic Random Access Memory. Okay, for the next slide, I need to present is importance of cache memory. First one, cache memory is faster in comparison to main memory and the secondary memory. What is main memory and secondary memory? For the main memory, as known as primary memory, which is the part of computer that store current data, programs, and instruction. For the secondary memory, that is referred to the storage device and system used to store data persistently even when the computer power off. Okay, second one is program stored in cache memory can be executed in less time. That is the data asset time of cache memory is less than that of the main memory. For the last one, last important of cache memory is cache memory store data and instruction that are regularly used by the CPU. Therefore, it increases the performance of the CPU.
This is the simulation setup and chosen parameter for our programs. The tested program is metric multiplications. Cache mapping is four-way set associative. Replacement policy is LRU, FIFO, and random replacement. For cache size tested is 4, 16, and 64 KB. For block size tested is 16, 64, and 128B. Associativity is 4 blocks per set, and metrics collected is total accesses, hits, misses, hits or miss read, execution time. And this is part of the code that performing matrix multiplications. And this tree is key code section that prove set associative mapping. The first one is this formula divide total cache into multiple set, each holding associativity number of block. The second one, this selects which set a block belong to, and block address is distributed across number set. The third one, each set is a cache set which hold a DQ, double-ended queue of text. And this tree is referred to LRU, FIFO, and random replacement. This code is the cache size, block size, and replacement policy tested in this program. As we can see, this is the 4 KB, 16 KB, and 64 KB. And for block size is 16, 64, and 128. For policies is LRU, FIFO, and random. Now I will simply demo how our program works. This is our programs, and after a quick run, and this is the output. All of the situation will be tested automatically and print. And as you can see, this is 4 KB, 16 KB, and 64 KB. And this is the blocks, which is 16B, 64B, 122B, and policy. This is the accesses, hits, miss, hit rate, miss rate, and execution time.
For 4 KB cache, the LRU has the highest hit rate that is stable above 67.17%, regardless of the block size. The execution time of LRU is the highest among all policies, due to overhead from maintaining usage order. For FIFO at 4 KB cache, the hit rate is lowest among all policy, and the execution time is also lowest. Random replacement has a hit rate that is consistently in the middle range, and its execution time is the highest. Performance varies due to the random eviction strategy. For 16 KB cache, the policy LRU has high cache efficiency across all block size, very low miss rate due to the effect reuse of frequently accessed data. The execution time is highest among all policy for LRU, caused by the LRU policy's overhead. For FIFO, the identical hit rate to LRU across all block size, indicating the cache size is large enough, reducing the impact of eviction strategy. It has the fastest execution time due to simple queue-based replacement logic. After that, the random replacement also performs identically in accuracy to LRU and FIFO at this cache size. The execution time is slightly slower than FIFO but faster than LRU. At 64 KB cache, LRU has highest cache hit rate, same as with 16 KB cache. The execution time of LRU is the highest among all policy due to policy overhead. The improvement in hit rate with larger blocks. For FIFO, it has same hit rate as LRU, showing that cache size is large enough to mask policy impact, and it has the fastest execution time across the board due to simple queue-based logic. Random replacement has identically performance to LRU and FIFO in cache efficiency. The execution time is just slightly lower than FIFO. This shows that policy has minimal impact at 64 KB due to abundant space. For cache size increasing from 4 KB to 16 KB drastically reduce miss rate and improve efficiency. 64 KB offer no significant gain beyond that. The block size helps reduce miss slightly by improving spatial locality. Replacement policy mattered most when the cache was small. LRU gave the best hit rates, but FIFO offered faster execution due to simpler logic. The policy performed similarly at 16 KB and 64 KB. A 16 KB cache with 64 KB
64B or 128B block size provides an excellent balance of high hit rate and fast execution. LRU is preferred when memory efficiency is critical, but FIFO is better or of speed in larger cache size. That's all. Thank you very much.